I've given up. Like really, I've just checked out.
And it was like at this point, we don't really
Like
care.
I was like taking it yesterday, and I was like, I should be a lot more stressed out than I am.
So who are we missing? We're just
No, I'm
missing
just like,
Anderson.
This is fun to bubble. Like I don't know. Like, does not phase me. I'll probably get like one right on first response. It's fine.
All right, guys. So everybody got their calculator?
Of course.
You do not?
Lily, it's like calculator day on the thing.
Come on, Lily.
Lily.
No worries. In calculus, which is where most of you, if not all of you, are heading next year, you are going to have to know how to use your calculator for 4 different things. You're going to have to be able to calculate a numerical integral, which we haven't talked about, won't talk about this year. You're going to have to calculate a numerical derivative, which we are going to talk about. You're going to have to graph functions, which you already know or should know how to do. And you have to know how to solve equations using your calculator. Now, so far, most of what you've done is solve equations using quadratic formula or factoring, or maybe even some synthetic division if it got really nasty, where you pick away at the problem until it becomes more solvable. But you can do all of that with a calculator if approximating is okay. And sometimes your decimals are exact, sometimes they're not. But it's a really great thing, and it makes sense. You technically already know how to do it, but you don't think about doing it. This year's AP classes that I have are much better than in years past about doing that. I don't know if it's because I've hammered it in or not, but they think about it more naturally. But in past, people just don't. They just forget. But today I want to talk about how your calculator, even though it can't do product rules and quotient rules, and it can't write out the actual derivative function, it can calculate the derivative at values. So for instance, say you were given a really ugly function like y equals 3x times the sine of e to the 2x times the natural log of 4x minus 3. And I wanted you to find the derivative where x is 4. Okay, so if it was a calculator problem, and probably a little bit better than a third of your AP test will be calculator based. You'll be sitting there with a calculator in front of you. You do not want to go and try to do a product rule with this, right? Remember that bonus I gave you that had the F, the G, and the H, right? Where you have to do the derivative of one and then copy the other ones down, blah, blah, blah. That's what you have to do here because you have that part, and that part, which gets to be really tedious. And then when you're done, then you got to stick a 4 in. Well, you don't want to do that. Your calculator can let you. So let me walk you through, and it's pretty easy to do this. You just have to be careful when you type, and you also have to remember that the Inspire is weird at times. I haven't really got a feel for why it does this or when it does this, because sometimes it does, sometimes it doesn't. But like on an 84, you don't have to put a times in there. You don't. But do it with an Inspire, because every now and then it'll just wig out and not give you an answer or whatever. So get in the habit of going 3x times sine of e to the 2x times natural log of 4x minus 3. Get in the habit of doing that when you're typing that in here, and you won't have issues. And that's especially true when you're graphing stuff. So you have this in front of you, but I am going to switch over so that you can see my screen. And we're just going to go with that. So try to, what I'm going to do first is I'm going to calculate this derivative, and I've written the process down, but you can just follow along with me if you want. Here is my calculator, zoomed on in, finally upgraded and got one like you guys. All right, so here we go. I'm on the scratch pad. So if I want to actually calculate a derivative, what I'm going to do, like I almost do in any situation, is I am going to go to my menu button, because that's kind of the source of all goodness. All right, so when I click the menu button right here, you can see all kinds of different things, and one of your options is calculus. So I'm going to hit the 4 button for calculus. It's not like you really have to memorize this stuff. Just go to the menu button and start looking. You'll see the calculus. And when I click on that, it gives me numerical derivative at a point. Okay, now there's other ways to go about this, but this to me is the best way when you want to calculate it. So I'm going to hit 1 for that, and it asks me, what variable would you like? Now, this is a big deal here. A lot of times in calculus, you're doing functions in terms of t, like velocity at what time, position at what time. So you're not using x and y variables, but it doesn't matter. You can calculate a derivative. If you have a function that's y and t, use a t if you want, use an x if you want, it doesn't matter. So if you're in the habit of using x's, and that's going to be the default variable, use x's even if it's time. But just remember, when you solve for x, it means t. Are y'all with me on that? And even if you have we have weird equations in calculus where you have totally different variables. So what? Change x's to y's, y's to x's so you can graph. Change t's to y's, x's to x's, or whatever you want to do. Change them. Use your calculator to solve, but just remember what you made substitutions with, and it'll totally be fine. So right here, I'm going to do that, and then according to this problem on example 1, it wanted me to find the derivative when x was what? 4. So I type a 4 in here. And then it actually can find the second derivative for me also. So if you wanted to find the second derivative, which in calculus we talk about the second derivative as well as the first derivative, because it means something, which I can't share right now because somebody's taking the calculus test. But anyway, so right here, that particular situation, I could go down here and choose to do the second derivative if I wanted to, but in this case I do not. So I'm going to go down here, okay. And what this does is set up a template for you so that you can now enter in the derivative. Okay? Now I'm going to show you something else in a moment. Most of the time when you have calculator problems like this, you are dealing with free response questions, and a multiple choice question might be worth a point, 1.2 points. Free response question might be worth 9 points. So when you're working with your calculator on a free response question, a lot of times you're doing a whole lot with this one function. Like they might give you a velocity function and then ask you about position. So you might be doing something. They might ask you about acceleration. So you might be doing something, and you're using it over and over and over the given function. So a lot of times you don't really want to keep typing it in over and over because that's a lot of typing. So I'm going to show you a little trick, but in this class it's not going to matter too much because you're not going to use it that much. But in the future, sometimes if you graph the function, and you'll see this in a second, you can just pull in y1 and kind of just use a variable for it each time. But I'll show you that in a second. In the meantime, I would just come in here and type in 3x, all right? So 3x, and then again, like I said, it's kind of finicky about time, so I'm going to go times, and then trig sine of e to the 2x. So there's my e to the 2x power, and I'm going to get outside that first parentheses and go times again, and then I'm going to say control natural log of 4x minus 3. That is not 4x minus 3, and then I'm going to get out. I don't even have to get out of the whole thing. I can just hit enter at this point. And when I hit enter, I should get negative 168,038. And what did I just find?
You're in grade B.
Yeah, I always want to be in radians. In calculus, we are in radians absolutely all the time. And the reason why is because radians is a real measure. Radian, I don't know if you remember what radian is. Like if you take, you know how it's 2 pi all the way around the whole circle, which is 6.28? Well, if you take the radius, the length of it, and you lay it across the circle, that radius lays across a circumference exactly 6.28 blah, blah, blah times. That's why there are 6.28 or 2 pi lengths of the radius. That's why they call it radians. Degrees are completely man-made. It's just like some dude sitting on a boat one day went, hey man, how many degrees across? Let's go with 360, or whoever made the initial map when they were doing the poles. I don't even know, I haven't researched it, why they picked 360. It seems very arbitrary, but it is completely an arbitrary number, 360 degrees. So in calculus, if you are taking derivatives or integrals and you have this false value in there, this man-made arbitrary value, it doesn't fit with the math. Okay, it just doesn't sync. So you're constantly having to do these conversions to make it make sense. Well, calculus says we're not going to mess with that in high school and college. So we're going to stick with a pure form, and that is radians. So you will not use degrees at all next year in calculus unless you're talking about temperature. Literally, make sure your calculator is in radians. I don't know if you heard me say that to her right when I handed her her test. Make sure your calculator is in radians or it'll blow up every problem you have like this. Are you with me? Anyway, so that would be the slope. I just took the derivative of this function. So pretty steep slope right there. Very well, might be nearing an asymptote. Who knows what's going on right there? But a very, very negative, very, very steep value. Actually, negative would be this way for you. A very, very steep derivative or slope at x equals 4.
I think I did something wrong. I don't know what I did wrong.
Did y'all get that number? Okay, see what it did with you. Oh, no, you're better there.
I fixed it. I saw what I did.
Why is your... Oh, did you hit E here?
Oh, I might have.
Yeah. Okay, yeah, use the E function.
Okay.
Okay, that's another thing. Notice my E is dark right here. If your E is light, then you probably use the letter E. You want to use the E function. I say something funny. I start smiling. What did I say? Nothing? Oh. If I make sure you use the E function near the E button that has the exponent, I'm still smiling. What did I say?
Well, because now you're just like, I don't know.
What?
You're so conscious that you said something, so it's funny.
Okay. So it's a chain reaction now. Okay.
Yeah.
All right, so yeah, make sure you use E to the power. Are y'all with me? Now even more y'all's fun. E to the power. Make sure you use that and not the letter E on those. So those are little learning things that we'll figure out as we go. But let me show you, like, again, what if you had to constantly keep using this derivative? And you're like, crap, it's so difficult to type in. It's so tedious to type in. Now you might go, I don't care. It's not that bad. Well, when you have 15 minutes to do a problem, if you spend 2 and 3 minutes typing these in every single time, it becomes troublesome. So here's what I do, especially on a free response question where I'm probably pretty certain I'm going to use it more than once. I'll go and graph it. So I'll just go to the graph function, hit tab, and I'm going to type in 3x times the sine of e, the exponent e to the 2x power. And then I'm going to get outside and go times the natural log of the 4x minus 3. So I'm going to graph this. Now I have no idea, not graphing the derivative, I'm just graphing the function, right? I have no idea what this is going to look like. I might not even see it. Turns out I do see it. It's all over the place. And you can see because it's jumping up and down so much. That's why it's so steep there. That's why the slopes were so steep, because it's just zigzagging. In fact, I just made this thing up. I probably should have picked a more normal function, but I was trying to show you how when it's really tough to type it in, probably easier another way. Now, once I have this function typed in, right, I could go back. And now when I go to take the derivative, I could go menu, calculus, numerical derivative, come down here, type my value of 4 in there. And now instead, as I'm working with this thing, I don't have to type it in anymore because it's stored as my F1 function. So do you remember, I don't know what situation we were doing vars. Maybe it was regression or something like that. But if I go to my var button right there, if I click on var, you will see, oh, there's F1. So I can just go down there and grab F1 and hit enter, and it'll insert the function. Now I do have to type X in. So I'll go ahead and type an X in there. But this takes the whole function, throws it in there, and lets me take the derivative there. And it alleviates the need for me to keep typing it in. So if I wanted to integrate it, then I could come in here and go menu, calculus, numerical integral. And again, I could do something like, oh, the integral from 0 to 5, this is probably going to tell me undefined. And again, we're not doing integrals. But this would let me do a bunch of stuff. Yeah, error, I figure it was. It would let me do a lot of different things without continuing to type in that equation over and over and over again. You know with me on that? Plus, it'll also, now that I have it in there, I could graph the derivative function. Like for instance, I could come back to here. That's the function. And again, sometimes because I picked a really ugly graph, the derivative might be really ugly. But look, I could hit tab and I can actually graph what the derivative looks like. Now remember, every time I take a derivative, I get a new function, right? After doing the product rule, the quotient rule. Well, that new function is going to look different than the old function, right? So I could come in here and graph it. Now, here's the problem with graphing it. When I graph it, I want to graph it over every single x value. I don't want to graph it just at 4, okay? Like we found the derivative just at 4. So the calculator anticipates that, and look what happens when I go to menu and I try to go to calculus again. It's not there. And they didn't put it there for a reason. They didn't put it there so you would not grab it, because when you grab the integral that shows, I mean, the derivative function that shows up when you're calculating, it always has that x equals blank for a certain value. So if I was ever trying to graph a derivative, we're not going to do it through that. We're going to go through our book button. Remember, the book button has a list of everything this calculator does. But to the left of it, it has a shortened menu with just a couple of options. So it's quicker to go to the left side of the book button. And if I click on that, you're going to see this little drop-down template. And if I go to right there, you see it? And yours might be in a different spot, but it says ddx of blank. That's the derivative button. Now don't grab the d2 over dx squared. Don't grab that. That's the second derivative. But this one right there, and yours might be in a different spot, especially if yours has a black face. But do y'all see this ddx? Like if your calculator has a black face, which is what most of mine have. The ddx right there, I'm going to click on it. There's my ddx, and I can go up here and insert the function. So I'm going to graph the derivative of the function. And we do that a lot in calculus. So I'm going to go again, vars, go grab my f1 so I don't have to type it in, f1 of x. Now again, this might get ugly. It's going to be in red. Might take a little bit of time. Yeah, there it is. So these are weird graphs. Most of the time, like if you have a parabola function, the derivative is going to be a line. It's more simple. But again, I made this one really ugly to show you how nice it is to not have to keep typing it by doing this way. And now if I wanted to find the derivative at x equals 4, check it out. Menu, trace, graph trace. How about this? Menu, trace. Yeah. Graph trace. And then if I hit at 4, it should spit out. Oh, I'm on the wrong function. Okay, hold on. Menu, trace. It's trace all. 4. Okay. Clearly my function is a little too rough for it right now. Its brain is still thinking. But anyway, the point is, if you had a simpler function on there, you could go use the derivative function and find that ugly value, that negative 168,000, whatever it was. You could find that using trace or any number of other methods that we would be able to employ in calculus. But anyway, I wanted to show you could do that. Also, for the same problem, what if they turned around and said, hey, I want you to find the second derivative. This is example 2. Well, again, second derivative, I could come up there and go menu, calculus, numerical derivative. And again, I'm going to find it at this time at x equals 1. So I put a 1 in there, but I don't want the first derivative. I click on it and I go to the second derivative. Okay, and I can do the second derivative of this function. And if it's already typed in there as y1, why not use it? So I could just come down here and go vars f1 of x, and it'll spit out the second derivative. And you'll find that second derivative has a different meaning than the first derivative. We know the first derivative is slow. Second derivative have a different meaning. We'll get to that when you take A, B, and BC. I'll track with me so far? Okay, so I want to talk about a couple of other things. So like if you look at this third, I think it's example 3. Yeah, example 3. It says for the given function, determine when the derivative of f is equal to 0. I'm sorry, is equal to 10. So now I want to determine, here I'll pull this back up. Okay, so this is asking now on example 3, determine when the derivative of f, which I don't even know yet, when is the derivative equal to 10? Okay, now I could do this the hard way, and people do this all the time. This would be a product rule, and I have people come in here and say, well, the derivative would be first derivative of the second part, and what's the derivative of that? Copy it on the bottom, derivative on the top, plus second part times the derivative of the first, which would be a times 3. I could put that here. And if I want to know where the derivative is equal to 10, I have to solve that. Well, we don't have the algebra to do that, do we? I mean, I don't know how to do that algebraically. You don't know how to do that algebraically. And this is where your calculator comes into play. This would show up on a calculator section, and nobody wants you to do it algebraically. So what you're going to do, and this is true whether you see x's in here, t's in here, because sometimes you're finding the derivative of t. It doesn't matter what the variables are. Turn it into a function. Like literally come in here and go, all right, I'm going to make the variable I'm trying to solve for x. And then I'm going to just move this to the other side, right? So I take this situation and I move that 10 over to the left and set it equal to 0. Still a function, right? I mean, still an equation, right? Yes, no? And then I say, I'm going to graph y equals that. And then I'm going to find the zeros of it. So if I just change that to y so that I can graph it, which would be F1 for you guys. If I change that to y or F1 and graph it, then I can just find out where it hits the x-axis, because where it hits the x-axis is when your y is 0. And that is a huge thing you have to be able to do in calculus. All right? So, but the great thing is, with a calculator, I don't even have to do this, because I took the derivative manually. My calculator knows how to do that. So really, if all I really have to do is say, okay, if this is f, all I want is to take the derivative of f. You with me? Take the derivative of that and find out when is the derivative equal to 10. Isn't that really what I'm asking? So all I have to do, if I really want to trust my calculator, is move the 10 over to the left. You tracking? And change that to y. And my calculator will let me graph y equals that. Literally, we're going to have that in our calculator. And let it do the work. And then I can just find the zeros. So let's check this out. I am going to get off this page and go back to the screen. All right, and I'm going to go to my calculate and get rid of all that junk that was in there. Oh, by the way, if you triple delete, this thing's still thinking. If I hit delete, 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 yeah, it says, do you want to delete everything? Yes, I do. All right, and if you don't like that window right there, go to Window, Standard, and it'll give you a nice standard normal window. So here's what I'm going to do. I want to graph this. So the first thing I'm going to do, because I might need the function, is I'm just going to throw the function in there. So the function was 3x times the natural log button. Don't hit LN, but you might be able to, but I just hit the natural log function. And then 4x minus 3. So there's my function. Okay? I don't really need it, but what I want now is I'm going to now graph y equals the derivative minus 10. And remember how we got that? We were trying to find out this is what we were doing. We were trying to find out where is the derivative of this function equal to 10? Where? So I move the 10 over, gives me an equation equal to 0, but then I'm going to replace 0 with y. So I'm going to actually graph now y equals, and I'm going to go to my book button, grab the derivative, put an x down there, so it's ddx, and I'm graphing the derivative of f1. That's my original function. Now, if you didn't already type it in as f1, that's fine. You could type it in now if you had not already done that. But again, I kind of anticipate that I'm going to be reusing this function a bunch of different ways. So that's why I'm doing that. So I'm going to go vars f1 of x, and it's going to now graph the derivative function in red. And tell me why you think you don't see that. Yeah, what were the derivative slopes, right? What were the slopes right here? What do you think the slope of that is? Pretty freaking big, right? So it's way up there. And the slopes probably don't even start getting smaller until it starts bending a lot, right? So these slopes are way, way up high. Doesn't matter. I've got this. Now, that's the derivative right here. You know what? I forgot to do the minus 10. That's the derivative function. I forgot to go minus 10. So I'm going to go minus 10. And I'm going to hit enter. So there's my derivative function minus 10. Okay? So this is me solving for where the derivative is equal to 10. And all I have to do is actually go in here and find out where that thing hits. Where is y0 here? And I can do that using my trace, not my trace button, but my solve for the zeros button. Is that making sense what I'm doing? Yes, no? Shake your head no if it's not. Okay, so I'm going to go menu now. I'm going to go analyze the graph. There's my 0 button. And I go in there and say, which graph? I want this red one. So I click on that and I can go, all right, left bound is there. And I come over to the right, click on that, and it gives me the first value, which I can't really see. So I'm going to grab that. We always round to 3 decimals when they're in AP Cal. They actually let you round or chop. I call that truncating. So you could round it. This one rounds and truncates the same way. But either way, you always use the 3 decimals. And then I would go back and go menu, analyze, 0, which graph, this red one. And I'd come over here and go left bound and then right bound. And I would grab the other 0 since I can't really tell what it is and move it up where I can see it. And this one would either truncate at 2.374, but most people would round it to 2.375. And those would be where x was, where the graph, the derivative of the graph was equal to 10. And that seems like an arbitrary thing to do, but a lot of times they'll say, hey, at what time did your velocity hit 50 miles per hour? All right, so I want to know, hey, at what time, I have this velocity function. Say I'm in physics, and I want to know at what point did I get it, how long did it take me to get to 50 miles an hour? So I'm solving for that t value. So I set the velocity equal to 50, right? But how do I solve if the velocity function is really ugly? Well, I move that 50 over, type it in as an equation, and I search the zeros to find time. And it's super easy to do this once you get in the habit. You just have to break out of this. What are y'all, juniors? How long have y'all been solving simple equations? Since like pre-algebra in 6th, 7th grade? You've been doing this now for 4 or 5 years. It's like, oh, I got an equation I got to solve. Where's my quadratic formula? But if it gets ugly and uglier, we can't do it. We don't have the math for it. Isaac Newton didn't have the math for it. That's why he created calculus. He did all these approximations to solve these. We now have a calculator. We can take it much more easy on ourselves if we just remember to use it. Okay, other things that they want to ask you about, where is the function decreasing? Where is the function increasing? And this is where your brain has to be retrained as well. Now, I want you to go back to this. All right, guys, some of y'all need to stick with me. I can sense you fading. Okay, so look at this one. This says, determine where the g function, this is example 4, where is the g function decreasing on the interval from -10 to 10? Now, do y'all know what decreasing means? Means what? Means it's going down from which direction? As you move from left to right. It means the y values are getting smaller. Now, a lot of you think, oh, I don't need calculus for that. I can graph it. I just graph it, look at it. I can see, oh, there's the decreasing. But you need to find over what interval. So how do you find the x-coordinate and the y-coordinate where it's decreasing? Anybody got a guess? Hypothetically, say here's your -10, here's your 10, and say your graph's doing something like this, right? And you can see right here that it's decreasing all on that interval right there, right? But if I want to know where, I'm asking like over what x values, where, I know it's right here and right here, but how do I find Those x values. You want to find the min and the max, right? Now, did I use any calculus to do that? But AP would want to know the calculus of it. Now, the way they mess with you, because sometimes on a multiple choice question, there's no way to know how you do things. What they do is they make it with a graph. You go to graph it to find the mins and the max. By the way, if you didn't want to use calculus, you just graph it and you find the max and the min there. And when it wouldn't be necessarily a max, but it could be a relative max, a high spot in that location. And that might not be the absolute min, but it's a relative min. And if you found those 2 points, couldn't you borrow their x coordinates and do the interval there? And that would make sense. And people do that. What AP does to mess with you, when you go to graph it, you don't see the graph. And you're like, oh, well, it's probably up a little bit. So you move it up to y equals 20. You still don't see it. You move it up to y equals 100. You still don't see it. You move it up to y equals 1,000. You don't see it. You move it up to y equals 50,000 and you don't see it. And you're like, what? I must have done something wrong, and you quit and you move on to something else. And there it is sitting up there at about 100,000. You're like, did they really want me to go hunting for the graph? And it would be some graph you have no idea what it's going to look like because you're not familiar with it. So they don't want you to do that. That's pre-calc. They want you to use the derivative. Now think about it. If I ask you where a function is decreasing, what are the slopes of a function on a decreasing section? They're less than 0. They're negative, right? So if the slopes are negative all through here, what if I graphed the slope function instead of the function? I know your brain hasn't done a lot with this, and that's what calculus is for, but I'm just showing you some things. And I'm not going to beat you over the head with this on this test, so don't worry about it at all. But the point is, if instead of graphing f, or in this case g, instead of graphing g, what if I graph the derivative of g? If I graph the derivative of g, what do you think the derivative of g looks like on this section over here, where all the slopes are positive? It would have to be above the x-axis. And where would the derivative look like here, where the slopes are positive? Above. So what that does is that takes a graph which the function might occur up there in the stratosphere, and it brings it right down to the x-axis. So you don't have to hunt for it. See, if I graph the derivative function, all I see now is the graph going where? Through positive values or negative values, and it's right there on the x-axis, and it's easy to tell what's going on. For instance, so I'm going to go to this. I'm going to delete all this junk out. Yes. Okay, so I'm going to type in the g function, x cubed minus 9x squared plus 14x plus 23. And you are going to see this one, I'm pretty sure. Yeah, there's your cubic function. You probably guessed a cubic function usually has those wiggles like that, right? So this is my function. And if I asked you now, where is this function? You cannot see that. If I ask you, where is this function decreasing? You could look at it and go, oh, well, it's increasing here. So it's decreasing there and then increasing there. But if I wanted the intervals, you'd have to find that relative max and that relative min, wouldn't you? All right, now you could do that. But watch what happens when I do the derivative. And I'm going to do the derivative right on top of this graph. You're going to see that all through here, where the function was increasing, the derivative is going to be positive. So you're going to see the derivative function above right there. And then starting up top where it starts decreasing to there, you're going to see the derivative have negative values. And then where it's increasing, you're going to see the derivative have positive values. So watch this. Tab, I'm going to graph the derivative. So again, book button, derivative, got to plug an x in, and I want the derivative of what? y1, the function I just had. I don't have to type it in twice, do I? So I'm just going to borrow y1 or f1, put an x in there, and here we go. Check it out. Everywhere, let me zoom out so you can see it a little bit better. Window, I don't know how that's going to go pretty high. How about up to, I don't need to go that wide. How about up to 50? Probably goes higher than that. Oh, wow. Look at you. Window. Okay, check it out. So here's the blue function, guys. Blue function, we were increasing to there, right? I'm going to bring this down. I'm increasing to there, and look, if that's the function, its slopes, which is the derivative, are positive. You see that? This function has negative slopes there, and the slopes are negative values. This function has positive slopes there, and the slopes are positive. You seeing that? And what happened right here and right here? What were the slopes of the function? And you can see the slopes right there. The slope function hit 0 because the slope of f is 0. Are you seeing that? Because the derivative of my function had a slope of 0, the derivative function was equal to 0. So when you graph the derivative function, it's really easy to just look at it and go, oh, if the derivative is negative, that must mean that the original function was decreasing. And I didn't have to go hunting for the graph. And they'll make you hunt a lot of times. But that's another example of what we might do. And now, to me, it's a lot easier to find those intervals because now I can just find the zeros of the derivative function. So I could come in here and go menu, analyze the zeros. It's going to ask me what graph. So I'm going to go to the second one, which is my derivative function. And I'll come in here and go, all right, the lower bound, that 0 was what, 0.918. So I'd say, okay, 0.918. And then I would come over here and say menu, analyze the zeros of this graph. And I'm going to say, all right, that next one is 5.082. 5.082. And you can say on that interval from this is 1/2, 1, from 0.9 to 5.082, that's where my function was decreasing. And you can see it. That's where the function is decreasing. That's where the derivative of the function is negative. It means the same thing. Now, if your brain's spinning about this a little bit, I totally understand. This is not going to be something that I'm beating you over the head with on the test. Again, I'm focusing on the derivatives, the mechanics of them, not the application I'm thinking of. Yeah.
Would the zeros be included in
Good point. No, actually they wouldn't. You're going to leave those open. And the reason why is at the top, it's neither increasing nor decreasing, is it? Right? So we say if a function is decreasing, it has a negative slope. And at 0 is neither positive nor negative. So we say it wouldn't be neither. So you're always going to have open circles on those intervals. Great question. Better than you even think. Really good. We can call those open intervals. But that's something that we'll talk about as well. That's 6 minutes. Also, just to talk about a couple other things. And again, I want to just throw this out here. Some years I don't talk about this. This is a topic, and implicit differentiation is a topic that I throw out occasionally. And I didn't do implicit this year because I feel like the calculator is a little bit more important to kind of start implanting that in your brain. But anyway, another thing we talk about is concavity. And concavity has to do with the second derivative. So like right here, this is what we call a concave up situation on a graph. And sometimes you'll have graphs, a lot of times that have concave up places and then concave down places. And this is an example of concave down. Some people say concave up, like a cup, because it could hold water, or concave down, like a frown, because it looks sad. But the point is, it doesn't have to be completely like this to be concave down. It could just be like a small section. Like that could be a concave down situation. A concave up could be just that. It doesn't have to be able to hold water, okay? So but a line is neither concave down or concave up. Well, anything that happens to be concave up on a certain region its second derivative is positive. So right here, the second derivative of a function would be positive there. Concave down, the second derivative would be negative. And if the second derivative is 0, then that was probably a linear situation where it didn't have any bend or concavity to it. So we will talk about concavity all the time. But like right here, if I said, hey, where is this function concave up? What do you know about concave up? The second derivative is positive. What if I graphed the second derivative function? And if I just graph the second derivative function, couldn't I look at it and tell wherever it is above the x-axis would mean what? That's where the second derivative is concave up, which is a lot better to me than graphing the function itself and trying to eyeball it because like right here, how do I know when it changes? I'm asking about concave up. This is a cubic function. So right here, this is concave up right through here, right? But where does it end? Like, where is that value? Like, if I'm looking for where, I'm talking about a region on the x-axis. It's hard for me to tell what that is. Does that make sense? I mean, I can't just eyeball it because you're going to look at this curve and it might look linear for a while. So what we're going to do is not graph the actual function. We would graph the second derivative function. So walk with me here as I show you that in example 5. That's probably all we're going to get to on this. But here we go. I could take this, delete. Is this the same function? Oh, it is. Sweet. So right here, I could come in here and say, all right, tab. I'm going to come in here and get rid of this. I'm going to actually go book button, but this time I'm going to use the second derivative button. See that? D2. I'm going to grab the second derivative, come down there and go dx, and I'm going to type my F1 again. And you can see how nice it is when I have F1 in there already. I don't have to keep retyping it. And look, I can see that the second derivative was actually linear. And I want to know where it's concave up. So what's concave up mean again? Well, the second derivative was positive. You can see it started being positive right there and went up, right? So I can actually take this, find that 0, and go menu, analyze the zeros. I can come in here, pick that graph, and go, all right, from what looks like 3 to infinity, or 3 to whenever the graph ended. In this case, it didn't really give me an ending. So I would say it looks like we're concave up from 3 to infinity, right? Now that looks like a problem I could have probably taken the second derivative of and set it equal to 0 and solved. It probably would have been simple, but your calculator becomes a huge resource if you can train your brain on the calculator section to not feel like you have to do the algebra. Y'all with me? Hey, I've given you some problems. See what you can do on them. There's probably some things we didn't cover, like I'm pretty sure there is, because we didn't even talk about velocity and acceleration and all that. So what I didn't get to, I'm not going to worry about. Okay.
For almost all of it, when I like looked up when you're teaching this, I was like, I have to test them how to connect the relationship. Like, you don't even use your calculator, you test them in like
Yeah.
make sure I have.
Cool. Hey, good luck this weekend.
Thank you.
All right, track guys, good luck. Y'all excited? It's supposed to be sunny at the beach?
Not at the beginning of the week, but not towards the end.
Yeah. Who's your main competition?
I actually just got a text from my coach saying that my main competition from Mountain has gone.
No. You kind of always want to go.
Yeah, I know.
You been?
I can. We've been back and forth all season, so it's gonna be a good race.
Or is he going to try to run?
I guess. He said he's now, but I would be surprised because he ran last year. I don't know if he's come down.
Well, you don't want to get hit in your spleen, but like if you fell hard or something, it might not give it.
I guess so. But I don't know if I'll say. But
I
there's
know you're
another.
exhausted. I know that.
And there's another guy who's pretty good. He's been valley, but doing this good.
Yeah.
You didn't sing.
Sure, get that friend of mine ever call you?
Sure.
About tutoring?
Yeah.
You did?
Mhm.
Have you been?
I have been.
Good.
I like it.
Good.
They're really nice.
Yeah. He went to Homewood. I don't know if you knew that.
Oh, really?
He's an 87 grad. You can find him on the wall. He has hair. That wall of fame that has all the pictures. Yeah, he's a pretty big time architect now.
Oh, cool.
Yeah. Anyway, good.